In this video, we're going to take a look at a really interesting relationship between one of our special discrete random variables and the most recently discussed continuous random variables. And so you can actually think of this as an application to one of the discrete random variables that we've talked about. And in fact, this application that I'm about to describe is probably one of my favorite ones that involve not just the Poisson distribution, but also the gamma distribution. So it's a nice um, way to illustrate that you can have a discrete process that also could lead into a continuous process. So they don't have to be separate and apart, right? Now, I'll preface this by saying the proof of the theorem that I will state in a few minutes is beyond the scope of what would be typically covered in a course like this, right? But we can certainly understand and use the theorem. I just can't give you the formal proof. It's a little bit advanced, right? But let me sort of describe this process. And so remember what the Poisson random variable does, right? You know, like on average, how many times an event happens in a certain interval of time or space, right? So let's say this is our time interval, and we have some reference point, so 0. And then of course we have intervals of time, so maybe we have like intervals of an hour. So you have the first hour, and then you have your second hour, and then your third hour, and then the fourth hour, and so forth. And now what the Poisson random variable count, so our Poisson RV, it counts the number of occurrences. Let's say again, we're doing things hourly. It counts the number of occurrences within an hour, right? And something like that, right? So for instance, if this is now the process in play, then in the first hour, my Poisson random variable would return a value of 3, right? The x's indicate, the blue x's indicate every time this event occurs. And then in the second hour, I remember because of independence, whatever happens in the first hour, it's almost like you forget about it. You have no memory of what has happened before. And whatever happened in this interval is not going to affect what happens in this interval. In the second hour, then it would return a value of 2 because there are 2 occurrences. In the third hour, it would return a value of 0. There are no occurrences. And then in the fourth, 3, the random variable would return a value of 3, and so on. Right? And that's like the counting process, right? But there's something else that's interesting as well. So let's say, again, from this reference point, suppose instead of counting the number of occurrences that took place in a set interval of time, what if you started a stopwatch and you measured the time until the next occurrence? So, you might ask the question, how long until, oh, well, I don't know why I was writing unit there, but how long until the next occurrence, right? And the thing is, we don't know, right? Because it's random. We don't know when the next one's going to come. Or, let's say the next occurrence. And then maybe you want to measure the time until the next 2 occurrences or 3 occurrences or 4 or 5. So again, what if we're now measuring the time until, right? So again, how long until the next k occurrences occur or happen, right? So we have a counter. So it's like we have two things in our and we'll have, on one hand we have the clicker that we click every time we see something happening. And then on the in the other hand, we have a stopwatch that we start right from a reference point, and then let's say we're measuring the time until the next three things occur. So we watch and we see one, and then we see another, and then we finally see that third, and then we hit our stopwatch and see, how long did that take, right? So again, you can be counting the number of things that's occurring, and you can also be measuring the time until a certain number of occurrences happen, right? And it turns out, what's remarkable is if you have a Poisson process, then the time until the next k occurrences, right? That time is actually a gamma random variable, which I think is just fascinating. Because a lot of times it's like, why are we studying all these different, random variables? And there are a ton of them out there, right? What's so special about I think everyone kind of agrees that the normal distribution is important, right? The more you study probability and statistics, you kind of get it. You're like, yes, I can see the importance of this. But like a gamma distribution, it requires this obscure function, this gamma function that, okay, who really cares about the gamma function? Well, lots of people do. It's really remarkable, again, where all that gamma function shows up. A lot of theoretical physics, sometimes in advanced engineering research, you see gamma functions show up. But I think this is just a simple process that we're describing, right? And it turns out that the time, again, until a certain number of recurrences, that time is a gamma distribution. So let's go ahead and state the theorem, right? I could give you kind of a heuristic proof of why the time until the next one, if you look at just the next occurrence, that would be a special case. So the next occurrence would be a special case, which would be the exponential. I could kind of give you a heuristic argument for that. But again, even that is a little lengthy. So we're going to forego that. Hopefully, at least the description here is really clear as to what it is, what is the relationship between the blue discrete occurrences and then the red time interval that we're measuring, right? So here's our theorem, right? And it basically, it describes the distribution of the waiting time between Poisson events, or you could say until a certain number of Poisson events occur. So here's our theorem. So let x be a Poisson random variable with mean time or expected time or average rate of occurrence with the mean of lambda. Remember, we use that parameter lambda for a Poisson random variable. If t, so I'll use this notation, t for time. So if t sub k represents the time until the next k occurrences, right, of this event, whatever it is, right? So if we're now measuring the time until we see this number of events occur, then it turns out that, so then this random variable, this time random variable, is a continuous random variable, and it follows a gamma distribution where alpha is the k, right? So alpha is the k value, and the beta happens to be 1 over lambda. So 1 over lambda, right? And yeah, there you go. So that's the result. It's pretty easy to state. It's how do you derive this? That's a fun and definitely not a trivial exercise. But it's definitely a result that can be utilized quite easily. So let's look at an example of this, right? So suppose people arrive at an emergency room at a rate of 5 per hour, right? Governed by a Poisson process. All right, so the number of people that arrive at this emergency room is a Poisson process, and that on average, because remember that's what the lambda is. This is our lambda. Lambda equals 5 people per hour. That's the average number that we would see in a given hour, and that's our parameter. So now let's ask ourselves a couple questions. So part A is this. What is the distribution of the time until the next person arrives? So until the next person arrives at this emergency room, right? Well, what is the distribution? Well, we use our theorem. Now, because it says the next person, then that means our k is equal to 1, because you're just waiting until that next person shows up, right? So the next person here, this means k is equal to 1. And then my 1 over lambda is 1/5. So actually, let me state it like this. So our alpha, which is our k, is equal to 1, and our beta, which is 1 over lambda, in this case is 1/5, right? Now, since alpha is equal to 1, this is that special case of the exponential distribution. So there are two ways we could say it. I will use, so t sub 1 to represent the time until the next person. We can write it like this. We could say that it is a gamma random variable with parameters 1 and 1/5. Or we could say it more simply. We know now that when alpha is equal to 1, we get that much simpler distribution, the exponential distribution with parameter 1/5, right? So let's write down the PDF of t1. So I'll use little t as my variable, and it will be, so for the exponential now, so remember it's 1 over beta times e to the negative x over beta, and then that in this case is valid for when t is greater than or equal to 0, and then 0 otherwise, right? Makes sense, since we're, as far as we're concerned, we're only looking forward. Time can't be negative, so a lot of this makes sense. Now we have all these reciprocals here. Well, let's simplify it, because 1 over 1/5 is 5. and then that's 5 times e to the negative 5t. I need to change that x to a t. I almost made it without mixing my variables, but there we go, t. So then that's negative 5t, and then that's for t greater than or equal to 0, or 0 otherwise. All right, so that's the distribution. And not only that, but we can write down, because it's exponential, we can actually write down the CDF, right? Isn't that cool? So we can write down the CDF. We have our formula for our exponential. So in this case, it's going to be 0 when t is less than 0. And then it's 1 minus e to the negative 5t when t is greater than or equal to 0. So that's the distribution of the time. Now what if, let's say we wanted to compute a couple probabilities. So let's say, what is the probability? So what is the probability that the waiting time until the next person arrives, let's say it exceeds 1.5 hours. It's just going to take us at least 1.5 hours to see the next person showing up. And that would be some record. I mean, 1.5 hours between visits to an emergency room. I mean, maybe, you never know. Right, so let's see if we can compute this. So this is the probability that our T1 is greater than 1.5. Okay? Well, I mean, let's apply our complement rule. Why would we want to do that? Well, for two things. It avoids having to deal with an improper integral, right? And we have the formula for the CDF, right, which requires us to compute probabilities where our random variable is less than or equal to a number. So this is 1 minus the probability that T1 is less than or equal to 1.5. And then by definition, what do we end up with? So we got 1 minus 1 minus, so now I'm just evaluating my CDF. So this is e to the power negative 5 times 1.5. So that the ones cancel out, the negative makes that a positive e, and then multiplying the exponents, we have a negative 7.5, right? So that's pretty small. That's pretty small, and that comes out to be 0.0006, right? So again, and this just from a practical standpoint, it makes sense. If our Poisson process on average sees 5 people per hour, it would be very unlikely that we would have to wait more than 1.5 hours to see the next person arriving, right? Yep. So again, we can't really say specifically that, okay, yeah, it's 0.0006. Yep, that makes sense. But we would at least expect that this number to be small. We wouldn't expect it to be like there's a 90% chance that you'll have to wait more than an hour and a half to see the next person arriving, when on average we observe 5 people arriving, per hour. All right. So that's one example. Let's look at another example now. So instead of just the next person, what if we're interested in like maybe the next 3 people? So let's do a couple questions similar to the first two. So what is the distribution of the time until the next three people arriving at the ER, right? So what is that distribution? Well, this is now it turns into the gamma, right? Because we're waiting for more than one person to show up. So in this case, my alpha, which is equal to my k, that's equal to 3, in this case, 3 people. And my beta is the same. So the beta is the 1 over lambda, which is the 1/5, right? And then, so let's now use, I'm using this notation, t sub 3 for the time until the next 3 individuals show up. And that, by that theorem, is a gamma distribution with parameters 3 and 1/5, right? So again, let's write down the PDF. We don't have a nice formula for the CDF for the gamma. Man, if only, right? Well, let's write down what we can write down. So again, I'm using little t for time. And let's see. So we got to use our formula for the PDF of the gamma. So it's 1 over beta to the alpha, so like that. And then times gamma of alpha. So we have this here. So alpha is 3, and then we have times x to the alpha minus 1, and then we have our e to the negative x over beta, which again is 1/5. And this again is valid. Oh, keep writing x, but it should be t. So well, let's get that. That's t. That's t. Right? And then that's valid for t greater than or equal to 0, and then 0 otherwise. All right, so that's what it looks like. Well, let's see if we can simplify this. All right, so let's go ahead and simplify this carefully, right? So let's give ourselves some room. So what do we have here? So 1 over 5 cubed is 1 over 125, but then you're taking the reciprocal of that, right? So you're going to end up with 1 over 25 on top, right? The gamma of 3 is 3 minus 1 factorial, so that is 2. That's going to be in the denominator, so we'll have a 2 there. And then we'll have t squared, and then we will have e to the negative 5t, and again that's valid for t greater than or equal to 0 or 0 otherwise. All right, so again, not the messiest of functions, but any kind of probability that we want to compute now will have to involve integration by parts, right? But at least we have the distribution, we have the PDF. So let's do a part D of this question and ask this probability question. So what is the probability that the waiting time until the next 3 people, so the next 3 people arrive, what is the probability that exceeds, let's say, an hour, so 1 hour, right? I mean, that doesn't that's not entirely unreasonable, right? On average, you'll see 5 per hour. So we'll see. Let's see what the math tells us. So we want the probability that our T3 is greater than 1, right? So again, if we were to do it as a greater than probability, then our limits of integration would be 1 to infinity, so we would have to apply our improper integral process. However, we can avoid that by doing our complement rule. So this is 1 minus the probability that T3 is less than or equal to 1. So we're going to have to integrate this function from 0 to 1. Right, so we have our 1 over 125 over 2t squared e to the negative 5t dt. Right, and then we have our 1 minus in front. So let's go ahead and do our integration by parts. And since we're going to have to do repeated integration by parts, I'm going to use my trusted table method. So I'll do my table right here. Now, let me do one more thing before I write down the table. Again, to avoid having too much stuff in my table, I'm going to factor out the 125 over 2 and then just focus on the t squared and the e to the negative 5t. Right, so we will do that. So we're going to focus on that part. So I'm going to use my u as t squared and my dv as e to the negative 5t. So I'm going to differentiate u 3 times. Why 3 times? Because on the third derivative, I'll get a 0, and that will help me a lot. So the first derivative is 2t, second derivative is 2, third derivative is 0. And then integrate the exponential function that many times. So negative 1/5 e to the negative 5t. 1 over 25 e to the negative 5t. Negative 1 over 125 e to the negative 5t. And then let's set up our product. So, this product, that product, that product. We can ignore the bottom product going across because that product would be 0. Because, again, technically, this will be the integral. We have to integrate v du, but we can ignore that part. And the other thing, too, just to make sure that we have these coefficients alternating signs like that. All right. So we can let's go ahead and just write down the expression and see what we come up with. We have the 1 minus and then the 125 over 2. Now let's write down the antiderivative. So it is going to be negative 1/5 t squared e to the negative 5t, and then minus 2 over 25. So minus 2 over 25 e to the negative 5t, and then another minus 2 over, but this time 125. So minus 2 over 125 e to the negative 5t, and then that my limits are from 0 to 1. And let's see, I think I left off, but yeah, there should be a t here. Yeah, because the powers of t should go down. T squared, t. In fact, let me write that more clearly. So this is a t, and then e to the negative 5t. All right, so there's our antiderivative. And so next up, and then what we can do, we can distribute this if we want. And so now that we've done the integration, we can distribute the 1 over 25, or the negative 1 over 25, or 125 over 2 can be distributed to the 3 terms here. So let's do that. So we'll have 1, and then this will give me a positive 25 over 2 t squared. Let's see. And then next up we have, so this will be another positive term. Oh, don't forget my e to the negative 5t, and then plus, and then we have a 5t e to the negative 5t, and then the negative 125 over 2 times the 2 over 125, so they completely cancel out, and we're left with a positive 1 e to the negative 5t. And again, this part has to be evaluated at 0 and 1. So I haven't evaluated yet. I was just kind of simplifying the coefficients by distributing. So let's go ahead now and plug in the upper limit. So we have 1 plus. So at the upper limit, when t is equal to 1, we end up with 25 over 2 e to the negative 5. And then plus 5 e to the negative 5, and then plus e to the negative 5. So that's at my upper limit. In my lower limit, now look at what happens. All these terms that have a t, they go away. And then e to the 0, as usual, is 1. So we got 1 there. Now, it works out. So let's see, what do we have? We have a 1 and then minus a 1 here, so the 1's cancel out, and then we have 25 over 2 plus 5, which is 35 over 2, plus 1, that is 37 over 2. So this boils down to 37 over 2 e to the negative 5. So that's the exact probability, and if we round, so this is approximately 0.1247. So, in summary, after quite a bit of calculus, we realized that the probability that the wait time until the next 3 people arrive at our ER is greater than an hour, that probability is 0.1247. So almost 12.5% of the time it's going to take more than 1 hour, right, for 3 people to arrive, the next 3. All right. So there you go. I think a pretty interesting application. It's one that I like because again it combines 2 of the really important special distributions that we talked about, right? The Poisson and now the gamma. So hopefully you found it interesting, and maybe, just maybe, you'll end up using it sometime in the future beyond this course. See you in the next video.